ISTB presents, in association with Dhanmanjuri Community College, DM University Imphal, launching a series of educational programs, recorded online classes for undergraduate and postgraduate students by teachers from various colleges and universities. During this COVID-19 lockdown, every day on ISTB Nongin, 8 p.m. from 24th May 2020 onwards. What's for that? Only on ISTB Nongin.
Good morning. We will continue our earlier discussion on random walk and binomial distribution. We have the binomial distribution. Pn of n1 is equal to capital N factorial divided by n1 factorial capital N minus n1 factorial p to the power n1 q to the power capital N minus n1, where capital N is the total number of steps taken and n1 is the number of steps taken towards the right, and the p is the probability of taking a step towards the right, and q is the probability of taking a step towards the left, okay, from any position. Okay. And if we plot this Pn versus n1, Pn1 versus n1, we find that it is distributed about the mean. And remember that binomial distribution is a discrete distribution. Binomial distribution is a discrete distribution, and today we'll discuss the conditions under which this binomial distribution reduces to the other distributions, say the Gaussian distribution and the Poisson distribution. Okay. So in this binomial distribution, if the number of steps, total number of steps n is large, then we find that this distribution, this deviation about the mean is very narrow. It's very narrow, and we can take this distribution, okay, to be a continuous distribution. And even though it is a discrete, and the number of step length taken is, the minimum step length taken is 1, and also this distribution exhibits a sharp maximum. A sharp maximum. So suppose that for this distribution we get a maximum in P n1 for n1 is equal to n1 tilde. Okay. Here we have, suppose that here we have this maximum, and then we will consider a region, okay, near this maximum, and the condition for the continuous distribution is another condition is that the fractional change in this probability, okay, distribution is very, very small. Okay. This fractional change, that is when the number of steps increases by 1, then the change in this probability Pn divided by the value Pn is much less than 1. Okay. And this is another condition for at which we take this distribution to be continuous. And so in order to find out this maximum, okay, so we must have the n1 of P of n1 has to be 0. It has to be 0, and d square, the n1 square of p of n1 has to be negative, okay? Has to be less than 0, and instead of taking this p, we can also take log of p, okay? The advantage of taking log of p is that this log of p varies rather slowly, okay? Slowly as compared to this p, and also when we expand, okay, by a power series expansion, this log of p, it converges much more rapidly, okay? So we can also take, instead of taking p, we'll use log of p, okay? We will use log of p. So we can expand, we can do a Taylor series expansion of this p about this maximum, okay? So p of n1, so I drop the subscript capital N, we do a power series expansion, so log of p of n1 is equal to log of p n1 tilde, okay, at n1 is equal to n1 tilde plus then n1 minus n1 tilde d n1 of log of p n1. This n1 is evaluated at n1 tilde, and plus 1 by 2 factorial n1 minus n1 tilde n1 tilde square d n1 square of log of p n1, and evaluated at, and this term is evaluated at n1 tilde, okay? Okay, plus the higher order terms n1 minus n1 tilde, okay? And as this log of p n1 is maximum at the point n1 tilde, this will vanish, okay? So what remains is log of p n1 tilde, and again because this is negative, okay, this term is negative, and we can write it as minus modulus of a, okay? We can write it as minus modulus of a, so we will have plus, so we can write down this minus n1 minus n1 tilde square a modulus divided by 2, okay? So let's call it as equation number 1, and this is equation number 2. Then p n1, so from this we can express p n1 can be expressed as some constant times exponential of e to the power minus n1 tilde square a modulus divided by 2. Okay, so let's call it equation number 3. Then let us apply these conditions, okay? In order to determine what are the constants and what is the value of this a, constant a, let us apply these conditions to the actual binomial distribution. So first, let us find out what is this log of p. So this log of pn1 is equal to log of capital N factorial minus log of n1 factorial minus log of capital N minus n1 factorial plus n1 log of p plus capital N minus n1 log of q. Then we differentiate with respect to dn1, with respect to n1, then log dn1 of log of pn1 is equal to, because this is constant, this will go to 0, dn1 of log of n1 factorial minus dn1 of log of capital N minus n1 factorial plus this is log of p and minus log of q. So let us find out what is this dn1 of log of n1 factorial. In order to find out this value, then we use the definition of the differentiation. Okay. Say dx of f is equal to, in the limit h tends to 0, f of x plus h minus f of x divided by h. Okay. And in this case, in our case, the h is the number of steps. So the minimum number of steps is 1. Minimum number of steps, minimum number of n1 is 1. So we will have the n1 of log of n1 factorial is equal to log of n1 plus 1 minus this factorial minus log of n1 factorial divided by 1. Okay, this is equal to log of n1 plus 1 factorial divided by n1 factorial, and this is equal to log of n1 plus 1. And since we are taking this n very large, we can also take n1 to be very large as compared to 1. So in this case, we find that this is approximately equal to n1 log of n1. So we find that this dn1 of log of pn1 is equal to dn1 of log of n1 factorial. So instead of this n1 factorial, I can write down log of n1. Okay. So I can just write down, I can remove this and write down is equal to log of n1 factorial, and for this I can write down, because there is one minus here and there is one minus here. Okay, so there must be one minus here, because there is one minus, so it must be minus. So I must have this must be minus. So this minus plus log of n minus n1, and then because we are and then plus log of p minus log of q. Here dn1 of log of n1 factorial is equal to log of n1. Okay, so this I can write down as log of n minus n1 divided by n1, and this by p n1 times q. Okay. So this shows that since we have this first derivative with respect to n1 is 0, okay, therefore this term has to be 0. Okay. This term has to be equal to 0. This implying that n minus n1 times p divided by n1 q is equal to 1, implies that n minus np minus n1p is equal to n1q. And again we are calculating this value at n1 tilde. Okay, this I have taken one step, so shortened one step. This at evaluated at n1 tilde is equal to 0. So I must have this n1 tilde n1 tilde, n1 tilde, and n1 tilde. Okay. This giving n1 tilde times p plus q is equal to capital N times p. Okay. We have n1 tilde is equal to np. Okay. That is the value of n1 at which the maximum of this probability distribution occurs is n1 tilde is equal to np, n1 bar. Okay. Then let us double differentiate this log of pn. Okay. So this probability distribution, from this we get p of n1 is equal to some constant times e to the power minus of n1 minus np square by 2, then a, then mode of a. Okay. So call it, so equation number 4. Then we have, so substituting the value of n1 tilde, we find this probability distribution given by this expression. And in order to evaluate this a, what is this a? A is nothing but the double differentiation with respect to n1 of this log of p of n1, and we have to evaluate it at n1 tilde. Okay. We double differentiate with respect to n1 log of p of n1 is equal to, so this is minus 1 over n1, another minus 1 over n minus n1, and these two terms go to 0, and we evaluate at n1 equal to n1 tilde. So this is to be evaluated at n1 equal to n1 tilde. This is equal to minus of n1 tilde is np, 1 over np, and then minus 1 over n minus np. This n1 tilde is equal to np. Okay. This is equal to 1 over minus of 1 over np minus, this is n times 1 minus p, this is nq, 1 minus p is q, so 1 by, this is plus nq. This will give us minus 1 over n pq, then p plus q is equal to minus 1 by npq. Okay. So this is nothing but our minus modulus of a. So this modulus of a is equal to 1 by npq. Okay. So this probability pn1, this is equal to a constant times exponential of minus n1 minus np square divided by 2. So a, instead of a, I substitute n pq. This is our probability density. If we want to find out this constant, the value of constant, then we'll have to use the normalization condition is that if we take this n1, if we define eta is equal to n1 minus n1 tilde, then the normalization condition is integral minus infinity to plus infinity p eta d eta is equal to 1. Okay, so this implies that, so integral minus infinity to plus infinity, this constant into e to the power minus eta square by 2 npq, and d eta is equal to 1. So for evaluating this integral, we have to use the standard, the Gaussian integral, which is minus infinity to plus infinity e to the power minus a square x square dx is equal to under root of pi by a. So using this integration, standard integration, we find that this a square, this is a square, so this constant times this a is equal to under root of 2 pi n pq. This is equal to 1, implies that the constant is given by 1 over under root of 2 pi n pq. So finally we can write down this p, this probability density p of n1 is p of n1 is equal to 1 over under root of 2 pi n pq to exponential of minus n1 minus np square divided by 2 npq. Okay, so if we compare this distribution, okay, with the standard Gaussian distribution, which is square by 2 sigma square dx, okay. X minus mu square by 2 sigma square. Then we find that this distribution, okay, which we have derived using the binomial distribution under the condition n is large and small n1 is also large, that is n1 is much larger than 1, and this under this condition this reduces to the Gaussian distribution with min mu is equal to np and standard deviation sigma is equal to under root of npq, under root of npq. So here in this diagram, this is the min, or this is our mu is equal to n1 bar, this is equal to np, and the standard deviation here is the standard deviation sigma given by under root of npq. Okay, thus the binomial distribution reduces to the Gaussian distribution when the total number of steps n is very large and n1 is also large. And if we compare this binomial distribution with the Gaussian distribution, remember that the binomial distribution is discrete, whereas this Gaussian distribution is continuous. And this when capital N is very large, then this deviation about the min becomes narrower, and we get the standard Gaussian distribution, which is inverted bell shaped Gaussian distribution, and which is symmetric about this min. Okay. And next, let us consider the case when this binomial distribution reduces to the Poisson distribution, P of n1, and I will just drop this Pn for sake of convenience. Then this we can write down is n times n minus 1, n minus 2, so on, up to n minus 1 times n minus n, here n1, okay, n1 is factorial, and p to the power n1, q to the power n minus n1 is divided by n1 factorial and n minus n1 factorial. These two terms, they cancel each other, and under the condition that capital N is much larger than n1, okay. This is going to be the condition number 1. Under this condition, we have this Pn1 is equal to n up to small n1 times, then p to the power n1, q to the power capital N minus n1, and here again I can remove, okay, this also, okay, this, and we have n1 factorial. So this I can just write down n to the power n1, p to the power n1, and q to the power n. Remember that q is equal to 1 minus p, so I can write it as 1 minus p to the power n. And again, there is another condition number 2, that p is much less than 1. Under this condition, we have e to the power p minus p is approximately equal to 1 minus p. So we can use this relation to write down, okay, here there must be one n1 factorial, so this is equal to np to the power n1, here p1 n1, so e to the power minus p times n divided by n1 factorial. So if we compare this probability density with Poisson distribution, that is p is equal to lambda to the power n1 e to the power minus lambda, or is n1, okay, factorial, okay. Or we can just write down px instead of this px e to the power minus x, this. So this is this p of n1 under the conditions that we have assumed. Capital N is much larger than small n1, and p, probability of taking a step towards the right, is much smaller than 1. Under these conditions, the binomial distribution reduces to the Poisson distribution. The Poisson distribution with the mean, I can write out with mean value is np. And remember that for this Poisson distribution is also a discrete distribution whose mean is equal to the variance. So let's finish here. Thank you so much.
ISTB presents, in association with Dhanmanjuri Community College, DM University Imphal, launching a series of educational programs, recorded online classes for undergraduate and postgraduate students by teachers from various colleges and universities. During this COVID-19 lockdown, every day on ISTB Nongin, 8 p.m. from 24th May 2020 onwards. Watch for that. only on IHTV Nongin.